Okay, I want to make one more video. I'm going to try to make it quick. If you'd like to put it on double time of another example like the one we did in class, and then additionally there'll be a Desmos activity that tries to give some visualization and connection for concavity. So for this one, I just want to focus on the increasing or decreasing intervals. Well, we'll see how much we want to do. So first of all, again, we have a polynomial, so the domain would be all real numbers. You see sometimes written this way, sometimes you see it like this, usually like that. Okay, so if I am not mistaken here, now what we could do is if we just want to find where it's increasing or decreasing, we're going to take the derivative. This one's not too bad. And we're going to set the derivative equal to 0. Okay, so we can find, so that means we're going to do 3x squared plus 2x equals 0 and find those values where that's 0, because those are the only spots where it can change from increasing to decreasing. So if we factor out an x, we get x times 3x plus 2. So x could be 0, or 3x plus 2 could be 0. Subtract 2, divide by 3, we get x equals negative 2/3. Okay, so let's test it out on the number line here. We have this value, we've got at negative 2/3 and 0 are the two values we found where now we're going to analyze the sign of the derivative to see if the intervals on which it's increasing or decreasing, because at these values it's 0, right? At negative 2/3 again, now it's 0. So what we could do is test this out. So maybe I'll try -1 here. So when x is -1, let's test it out. This would be a negative times a negative times a negative, right? Negative, which means a positive. So it's increasing here. F of x is increasing. Let's try a value in between these. We could try negative 1/3. We see here that negative 1/3 will give me a negative times a positive, right? This will give me -1 plus 2, which is 1. So this is negative. So it does indeed change from increasing to decreasing. And now let's try one over here. So greater than that 0. We know at those values it's 0, but those are the only possible times it could change. Let's try 1 greater than 0. So f prime of 1 would be a positive times a positive. So indeed, it does change from increasing to decreasing to increasing. So we could then say, just like we said on this previous one, part of our summary would be that we could say this function is increasing on two intervals. So we could say it's increasing from negative infinity to negative 2/3, not including those values, so I use my parentheses, and it's also increasing from 0 to positive infinity. And we also use a parentheses on the infinities because you can't really include infinity because it's not like a number, but that's another conversation for another day. And then, and then it's decreasing in between those two values. So from negative 2/3 to 0. And that's it for decreasing. So it's going to be going bam, bam, bam. The interesting thing is if we take this now, we could then find the concavity, and we would see that there's just going to be one possible inflection point. So the second derivative would be 6x plus 2. If I set that equal to 0, I'm going to get 6x plus 2 equals 0. Could divide everything by 2 if I wanted. 3x plus 1 equals 0. So the only 0 is going to be at when x equals subtract negative 1/3. Okay, so at negative 1/3, we could test now concavity here. So at negative 1/3, our second derivative is 0. So this is the sign. And we can see where does it have concave up, where is it concave down. So, and then what does it tell us about f of x in terms of concavity. So we could try, say, negative 1 and 0, I guess. Let's see. F double prime of negative 1. Or let me write my negative 1 is, as I did before, so it'll be 6 times negative 1. So this will be a negative, right? So here at negative 1, it is negative, so it's concave down. And then let me try, let's just use 0. F double prime of 0 is positive. So this is indeed concave up there. So this would be an inflection point where the concavity changes, and also where we could then say, add to our summary and say it's concave up from negative 1/3 to infinity. And then let me do this insert space here. And it's concave down, this function. The rest of the time, basically, and what we had seen negative infinity to negative 1/3. Here's the graph trying to demonstrate what it is we just found. So I put these vertical lines at negative 2/3 and 0 to show you first the increasing, decreasing. So we could see, indeed, it looks correct that our graph is increasing, increasing, increasing to negative 2/3. There it's got that little maximum. It decreases only between those two values till it hits that minimum and then increases to infinity. And if we look carefully, I also put a vertical line here we could drop. Here it's concave down, 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 down. The slope is getting less over time. But there is where we have what we call the inflection point, where it goes concave down, sort of as if water falling out, almost like the upside down cup. And then it transitions from the upside down cup to the right side up cup, where you could even imagine putting water in here, right? That's what we call the inflection point, where the concavity changes. Hope this example is helpful, and the Desmos activity, don't take more than, if it's going too crazy long, just stop, unless you're enjoying it, of course. But I'll see you all Thursday in class. Much love, everybody. Don't hesitate to reach out.